We're looking at position time graphs versus velocity time graphs. We said that on a velocity time graph, how high you are is your velocity. On a position time graph, how steep you are, slope is the velocity. And we looked at a couple of examples and then we paused here. Let's talk about acceleration. Example 1. What does an acceleration of 1.25 meters per second squared to the east or to the right mean if A, the object starts at rest, and B, the object is initially moving west or to the left or backwards at 2 meters per second? We're going to answer that in the next couple of examples. So I'm not going to answer that here, but that's what we're going to try to answer. We want to now, Amy, say, what if you're changing speeds? Because that's really much more realistic. Things don't go in a nice straight line at a steady speed. They speed up and they slow down. Acceleration is a vector. That's probably worth underlining. It has a direction. But Alexa, it's very difficult to visualize or interpret its direction. And the reason is, even my Physics 12s, even in university, kids confuse velocity and acceleration. And I can pound into them that velocity and acceleration are different, and then I can ask them another thought experiment that confuses them again. And the only way I know to do that then is to look at various examples. The direction an object is moving and the rate at which it's moving are both related to the velocity, but not to the acceleration. To determine the direction of the acceleration, we need to watch the object for a while and see how its velocity is changing, because acceleration is the change in velocity. We're going to start out doing this, Madison, with a chart. And then hopefully by the end of this lesson, if not next class for sure, I can give you the nice, short, wonderful equations where we go from charts and graphs and 2 pages of work to 2 lines of work. But you are going to need a good calculator. So you ready? Fill in the chart for acceleration is 1.25 meters per second squared to the east. So we're going to call east positive. Alexa, what we call west then? Negative, okay? Now, we could have done it the other way around. There's no rule that says east has to be positive, but since I put a plus sign in front of the 1.25, let's be consistent. So the initial velocity is 0. So at time 0, we're traveling 0 meters per second. Now, an acceleration of 1.25 meters per second means every second you're speeding up in the eastward direction by 1.25 meters per second. An acceleration of 1.25 meters per second, meter per second squared, means every second, how is your speed changing? You're gaining 1.25 meters per second east. So after 1 second, how fast are we traveling if we start at 0? You're right. We're still accelerating, so after 2 seconds, add a direction, east. After 2 seconds, how fast are we traveling if we continue to accelerate? Max, you're right. 2.5 meters per second. Direction. After 3 seconds, how fast are we traveling? Meters per second. Direction. Direction. East. What if instead of starting at rest, part B says, imagine your initial velocity is 2 meters per second east. Okay, so 2 meters per second east, that's what we're starting out at time 0. What's our acceleration? How big according to this question? 1.25 meters per second squared. What direction? East. So we're traveling 2 meters per second east, and we speed up in 1 second by an extra 1.25 meters per second east. What's our new velocity after 1 second? Is that okay, Justin? You awake, Justin? Okay. After 2 seconds, how fast are we traveling? Go ahead, Spence. 4.5. Apparently you can add decimals in your head. Be proud. Some people here apparently can. And after 3 seconds? And the speed would continue to increase. Okay? C says, now let's start out going 2 meters per second west. You know what? This whole east and west thing, putting a big capital E, has been very, very nice, but there's a much more convenient way mathematically, wow, to show east and west. How? You know what? Instead of writing 2 meters per second west, I'm going to say my initial velocity is negative 2 meters per second. That is west. Okay, so you ready? I'm traveling that way at negative 2 meters per second. I accelerate this way at 1.25 meters per second. What's my velocity after 1 second? Can you reason your way there? Now, we're eventually going to have an equation that lets us do this without thinking. But can you reason your way there? Devin. I'm still traveling backwards or to the west, but I've slowed down. So initially I was traveling really fast, but I'm slowing down. Okay? Now, over the next second, I keep accelerating this way at 1.25. I start out traveling this way at 0.75. So after 1 second, how fast will I be traveling? Spence, I think you said it. Yep. You know what? Let's put a positive in front just to emphasize that we clued in that it was positive. You don't need to normally put a positive in front of a number. I will assume that you meant it to be positive. But in our notes, Alexa, let's emphasize, hey, oh, you know what? You know what else I can tell you? Spencer, what was my speed at time 1 second? What was my velocity at time 1 second? Read it to me. What's my velocity at t equals 2 seconds? What can you tell me happened between 1 second and 2 seconds? What must have happened? 2 things. What can you tell me about my direction? Change direction. Now, think about it. If I was traveling this way, and now I'm traveling this way, what else must have happened for a split second between 1 and 2 seconds? Kyle. I had to have come to a stop for a split second. In the laws of the physical universe, that must be the case. Ooh. Okay, so now we're getting some interesting data. Oh, so now we're going 0.5 meters per second. How fast will we be going after 3 seconds? Now we're back to what we've been doing in part A and part B. We can just continue to add the acceleration. So now it would be positive, 1.75 meters per second. And after 4 seconds, it would be this plus this plus. Now, this is all great, this chart, but it'd be nice if to find the speed or the velocity at 4 seconds, it would be nice if I didn't have to calculate the velocity at 0, 1, 2, and 3 to find the 4th second. Or what if I had said, find the velocity after 19 seconds? Do I have to draw 19 squares? No! But this is to help us wrap our brain around what's going on. It is perfectly possible to have a positive speed and a negative acceleration. All that means is you're slowing down. Or you could have a negative accelerate speed going backwards and a positive acceleration. It means you're slowing down in the backwards direction and you're going to come to a stop and you're going to change direction and you're going to start going forwards. Velocity and acceleration do not have to be in the same direction. Now, eventually, they'll end up in the same direction because if you keep traveling long enough, you'll change direction and you'll go in the direction of the acceleration. But they don't have to be. Example 5 says, produce graphs of velocity versus time for example 4. Okay, we can do this for all of these. Now, let's see. I get a 3.75, a 5.75, a 1. You know what I'm going to do? We're going to do kind of a rough guess. I'm going to call right here 6 meters per second. 6 meters per second. 6 meters per second. How many seconds did we use up? So I'll put 3 right there, 3 right there, 3 right there, and then if I eyeball it, Spence, there's 1, there's 2, there's 1, there's 2, there's 1, there's... Yeah, that's terrible. I can do a little better with that. Okay, if that top one is 6, how high is that? Right here. 3. So let's put a 3 and a 3 and a 3. Below the x-axis, I don't think that's as long as above the x-axis, is it? I'm eyeballing it. You know what? Well, this is how you do, Oscar, a really rough sketch of a graph. Oh, that's terrible. If you're doing a rough sketch, you fill in the highest values, and then you divide it in half, and then you kind of eyeball dividing it into nice, even gaps. Okay. Okay. In the first graph, in A, let's call it A, B, and C, what was our speed? What was our velocity? Yeah. Quickly, Bunny. What was our velocity at time 0? From the chart, what was our velocity at time 0 in the first example in A? 0. Cool. After 1 second, how high were we? I'll eyeball it a little bit higher than my first hash mark, kind of right about there, sort of, maybe. After 2 seconds. Be about there. After 3 seconds. Yeah. Now this should be a straight line, but we're rough freehanding. But here's what I want to say. What is the slope? What's the rise? 3.75, right? Because that's the highest we got. What's the run? 3 seconds. Can someone go 3.75 divided by 3? You should get a number that looks familiar. Where did 1.25 appear in the question? No, what was the 1.25 in the question? Even earlier in the list of stuff that I gave you. Hey. If the slope of a distance versus time graph is the velocity, you know what would be kind of cool? If the slope of a velocity versus time graph was the acceleration. That'd be kind of cool. Let's see. You know what? For B, I'm just going to do the first point and the last point. First point, where were we? After 1 second, where were we? 2. After 3 seconds, where were we? What's the slope? Let's see. It's going to be 5.75 take away 2. There's my rise. Over 3. What's that on your calculator? Now, there's more than one number on the top, so you have to put the top in brackets. 5.75 minus 2 divided by 3, right? I'm just going rise over run. Tell me I get 1.25 again, do I? I should, because it's the same acceleration. Oh, I typed it in wrong. Tell me I get 1.25 again if I type it in correctly. I should, because it's the same acceleration. We're not going to bother doing C, but can you tell me what the slope of C is based on the data without actually doing any arithmetic? So, much like I highlighted a key idea in the previous lesson, well, no. Put your pencils down. You don't need to memorize. If you know slope is what over what? Okay, if you have rise over run memorized, you don't need to memorize the graphs. You can figure it out every time. Watch. If I give you a distance in meters versus time in seconds graph, what did you tell me slope was? What over what? Rise. Is rise vertical or horizontal? Vertical. What units are on my y-axis, on my vertical? You told me rise over. What units are on my run, on my x-axis? If you know that meters per second is velocity, if you go rise over run, you can memorize that the slope of a position versus time graph is the velocity, or in that one line, it stands out at you. What about a velocity in meters per second versus time in seconds graph? And if I say to you, hey, what's the slope? It would be rise over run. What's another way to write meters per second per second? And so my usual trick is, rather than memorizing graphs, I know how to do that with the unit. And I'm going to memorize the units because I have to memorize the units anyways to keep stuff straight. So you can memorize the two graphs. Kyle, knock yourself out. Go ahead. Or if you really want to embrace your inner nerd, you can derive it with that trick. If you guys want to write that down right now, you can. In Physics 12, I'll be giving you about 50 graphs. Nobody memorizes them. Oh, and in Physics 12, and actually this year, we'll also talk about the area under a graph, and there's an easy way to memorize those too. Got it? It's kind of a cool trick. It's got a touch of nerdiness, a touch of cleverness. All right, example 6. Turn the page. I haven't given you numbers. By the way, what variable am I using in the first graph instead of d for distance? Look at the first graph. What variable did I put on the y-axis? X for position, left, right. We said that was acceptable as well, just trying to get used to all the ones that are out there. So describe the motion in this position graph and then fill in the missing graphs. And assume if there is an acceleration that it's constant. Okay. What's going on right there? Positive, so positive velocity, constant velocity, or changing velocity. And remember, whenever I'm saying the word velocity on a position time graph, what are you thinking? A word that begins with the letter S and rhymes with Pope. So that first little section, constant slope or changing slope. What I'm really saying is it a line or a curve? So that first section, line or curve? Constant slope or changing slope? Constant velocity or changing velocity? How about like that? You could draw yours lower. I would give you full marks. You could draw yours higher, I would give you full marks. But if you drew yours slanty, I'd say, no. What's happening here? Constant slope or changing slope? Constant or changing? Changing. So constant velocity or changing velocity? You know what the fancy word for a changing velocity is? It begins with letter A. Acceleration. It's an acceleration. Now, oh, you know what? In fact, before we go on, let's do the acceleration graph. So here, if you're traveling at a constant velocity, is your speed or your velocity changing? So what's your acceleration? It's meant to be an obvious trick question. I heard someone whisper it. I heard someone say it loudly. Zero. In other words, if I wanted to graph the acceleration for this section, it would be a line 0 high. No acceleration as a number 0. Okay, so what's happening right here? Speeding up, slowing down, or constant speed? Speeding up. So I would look for a velocity that was getting bigger. You could draw yours steeper, I'd give you full marks. You could draw yours shallower, I'd give you full marks. But if you drew it flat, no. Or if you went downhill, no. I would be looking for something increasing. We have an acceleration. We have some kind of positive constant acceleration, something like that, maybe. Is that okay, Amelia? Hey, what's happening in this section right here? Constant what? I know slope, but what do we mean? Velocity, acceleration, distance, what? Okay, constant velocity. Compare it to my original constant velocity. Am I traveling faster or slower? Steep. Okay. Oh, and you know what? In fact, I think what I might do is I might just connect it right. Oh, yeah. Look. I started out going at a constant speed. Then I increased my speed. And then I leveled off and kept going at a constant speed. Did I say constant speed or constant velocity? What's my acceleration for this section right here? Sorry? Ah. Right? Okay. Consider the velocity time graph below. Okay. This is important. This is a velocity time graph. So when I see the slope on here, what's the slope telling me? Not velocity. What's the slope telling me here? Oh boy. What's the slope of a velocity time graph? Thomas? So, the slope of this is going to be the acceleration. Where does velocity appear on a velocity time graph? The height, how high you are. So A says, describe the motion. Oh, and I put numbers on here, so I can tell you this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, blah, blah. I haven't put numbers on the y-axis. Yeah. Quick like money. Says, describe the motion depicted on this graph. So let's call this section A. Let's call this section B. Let's call this section C. Describe what's happening in section A, the first 3 seconds. Are we at rest? So are we at rest? What would at rest look like? That right there, a line 0 high. Are we at a constant velocity? What would a constant velocity look like on a velocity time graph? All lines are straight, Captain Obvious. More specific. I know what you mean, but when you say straight line, you got to use a different word, because if it's a line, it's automatically straight. What kind of a slope would show a constant velocity? I'll give you a hint. A is not a constant velocity. Do you know how I know? Ready, Oscar? How fast am I traveling right now? 0. How fast am I traveling here? That fast. I must be what? Constant velocity? No. What am I doing? Accelerating. Forwards or backwards? Forwards. Forwards. In section A, we are accelerating forwards. Accelerating forwards. For how long? For 3 seconds. Now, right at time 3, are we going backwards? No. But what are we doing in section B? By the way, how do I know we're still moving forwards? Because my height is my velocity. Is my height above 0 or below 0 in section B? Above 0. So what would that mean as a direction? Forwards. But what's happening in section B? Decelerating. You know what? We could even say and I love your fancy word. D2Cs, Mr. Dueck. Decelerating. What about in section C? What do you notice about section C? Below 0. What would below 0 on a velocity time graph mean? Directionally, what would that imply? Going backwards. Are we speeding up going backwards or slowing down going backwards? We're going backwards faster and faster and faster and faster. See it? If I continue the line, after a few seconds, I'll be going backwards really fast. So section C, speeding up in the backwards direction. Speeding up in the backwards direction. Okay, let's answer part B here. Part B says, at what time does the velocity have the greatest positive value? What do you think? How many seconds in do we have the greatest positive value? At t equals 3? Good. C says, at what time does the acceleration have the greatest positive value? Now, where does acceleration appear on a velocity time graph? Slope. So really what this is saying is, when do you have the biggest positive slope? It's a range of times. Between what seconds? Go ahead, Danielle. Between 0 and 3. D says, ooh, at what time does the position have the greatest positive value? When have we traveled the furthest away from our starting point? Now, I always throw this out there, and then I'll model it, and you'll figure it out, but I'm always curious to see who can reason their way. Yeah?
Probably 5 seconds.
Probably 5 seconds? Convince me.
Because you're always moving forward until that moment.
Ah, did you hear him? I'm moving further away all the way up until t equals 5, and only then do I turn around and start coming back. Which means if I'm always moving further away, I may be slowing down, but I'm always moving further away. By the way, what happened right at t equals 5. What must I have done for a split second? Stopped, turned around. Stopped, and turned around. In fact, I think what we're saying is this. If this is 0, for 2 seconds I'm speeding up, then I'm slowing down. At 5 seconds I stop, and then I start to speed up backwards. And I might eventually end up back where I started from. I don't know. I might go further past where I started from. I don't know. But that's sort of the motion. It's like you're doing some kind of a drill where you jog forward, slow down, and then start running backwards. Lots of information. What's your homework? I said answer the following on a separate piece of paper. I think you can do these on here. Certainly number 1. Now, number 1 is just like the 1.25 acceleration that we did, except I'm already sneaking in the fact that actually when you drop something, free fall, the acceleration is negative 9.8 meters per second squared. It's not as nice a number to do math with in your head. Oh, for Pete's sakes, you got a calculator. See if you can do number 1. I'm not going to freak about 1B. See if you can get the chart for 1A. Describe the motion and produce the missing graph. I'm okay with part number 2. By describe, use words like, yeah. Can you wait till I assign the homework, please? Use words like forwards, backwards, speeding up, slowing down, increasing, decreasing, constant, rest, those kinds of things. Okay? So number 2, and also 2 part B. This one's a little tricky. Assume right here, by the way, that we're supposed to be touching the x-axis. In other words, assume right there is 0 high. What happens to the motion of an object if 3 is good? 4 is good. Obviously, don't do the ones that I crossed out. 6 is good. 7 is good. And you can pass on 8 and 9. And I think I got a little sheet to give you as well. So patience, those of you that are fidgety. So that for homework, and then the second assignment, for those of you that were away, is this little sheet here that I handed out called acceleration and slope. And for acceleration and slope, I got scrambled answers on the back. You should find them all there, I hope.